flat control systems. Okay, so the ultimate goal for both military as well as commercial aviation is must be the aircraft should be operated in all weather operations. Then how can it is possible to operate the aircraft in all weather operation means without a visual reference of runway, the pilot can be able to land or we can able to land the aircrafts. Okay, so if you want to achieve this, you must accomplished by a automatic landing system. It will guide the aircraft down a predetermined glide slope, and then I come to pre-selected altitude. Then it will go for a flare path. Then it will comes to landing to touch the touchdown points. Therefore, so from up to approach path to your descent to where landing fully automatic. Then we made with because some bad weather condition the pilot cannot see the visual reference of runway. So this will be engaged with your automatic landing systems. So the automatic landing systems we are using this Chennai airport is to be a ILS instrument based landing system. Okay, this has a three main components. One is marker beacon, then it's a glide slope coupler. That glide slope will be located in the end of the runway. It will guide the aircraft to the vertical reference. It will give the vertical reference to the aircrafts because there is a glide slope receiver that will be located in your aircraft. It will be guide your aircraft to your pre-selected altitude that will comes to. Then your localizer will be helpful to align your aircraft with your center line. The marker beacon will be indicates whether how much distance far away from the airport. There will be once the aircraft comes to nearby the aircraft, each marker beacon. Suppose if we are so far from 14 nautical mile from this airport, then maybe the outer marker beacon will be blink on. Now we will comes to very close to this aircraft. That based on that there will be light indication. It gives to the pilot. So we are in the so far from the airport from some nautical mile. So that information will be provided by your marker beacons. So this here the entire things we can in this section we will cover the longitudinal control portion of your such a systems. So this section we are going to address the design of glide slope coupler and automatic control system and altitude control altitude hold control system. All things one thing is common to control your flight path angles. So this automatic control of the flight path angle without simultaneous control of airspeed. So without controlling the airspeed, it is not possible to control your flight path angle. Whether you have to control the speed either manually or automatically. Okay. So if you design a coupler, if you come design your automatic landing system, you must concentrate on your velocity control of your aircraft. Whether you have to control the whether we have to provide velocity control through manual or through automatic systems. Okay, but you must control the airspeed of the aircraft. Okay, so this portion will today we are going to cover to discuss that is your glide slope. First we think is we take one basic autopilot system with that with velocity rate feedback. Then we discuss what is the need of a speed controller in this design of glide slope coupler. After that we couple with your glide slope coupler. Then we have to discuss your automatic flare control system also. So this is a longitudinal equation of motions. So this equation motion we already studied in aircraft stability and control. So we need to go for out we are getting that. We simply take that equations only. Okay. So this equation will be relate all these parameters. Okay. Where alpha is to be your angle of attack, theta is to be your pitch angle, then del E, that is elevator deflection angle. So this equation of motion will be gives your longitudinal equation of motions for these various design parameters. So now we take your basic autopilot of the jet transport aircraft. The landing configuration where the aircraft flies at the sea level is 200 feet per second. This is an assumption we made here. So these were basic autopilot for the jet transport aircraft, these landing configurations. So one is to be your is elevator transfer function, these to be your aircraft transfer functions. These aircraft transfer function, how we can obtain, we come from these equations. These equations or this equation, take any these two equation, this equation where del G is your input, where theta of S is to be your output. Okay, then we need to find out your the ratio of output is your pitch angle, input is your elevator deflection angle. So we get the aircraft transfer function. This for aircraft transfer function for longitudinal equation of motion. That is, it is called as a elevator transfer function. Elevator transfer function. Elevator transfer function. So in this case, we will put the velocity rate feedback. So we will discuss what is essential for your velocity rate feedbacks. Okay, that is where it is called as your rate gyrosensity. This S is called as your rate gyrosensity. Rate gyrosensity. Then it is a theta dot S. If we put integral, then we will get theta. Then it will come reference to a reference pitch angle. Whether you have aircraft, we decide where reference pitch angle or not. Suppose if you the aircraft flies a certain altitude with a decide a pitch angle. Okay, suppose if there is any gust or it will encounter, maybe the pitch angle will be deviated. That will be sensed by this. This is your basic autopilot for jet transport. So it will automatically sense where, then based on that it will initiate your voltage signal produced by the amplifier, that will initiate your elevator deflection. So this elevator, based on this, the elevator will be deflected, then we will get a desired pitch angle. Okay. So today we try to sketch the root locus for your inner loop of your basic autopilot landing configuration system. These were inner loop. This is your outer loop. Well, sketch the root locus for inner loop as well as outer loop for basic autopilot for jet and transport aircraft. Then we came to know that what is the essential for your rate gyrosensity. Why we incorporate velocity rate feedback. Then after that we try to sketch the response of the system with rate feedback, without feedback. Okay. Now these were inner loop having a transfer functions. One is elevator transfer function. So I take only the inner loop. So this inner loop is elevator transfer function. It is called as a minus 10 divided by S plus 10. Where aircraft having a transfer function is minus 1.2 S plus 0.585 divided by S square plus 1.5 S plus 1.47. From that I get theta dot rate feedback is given to here. This is the rate gyrosensity. Here we put rate gyrosensity as a feedback. That means we put symbol k instead of s, because here we is using the transfer function times s. Therefore, we need to avoid this confusion. I make it as a k symbol for your rate gyrosensity. Okay. So we try to sketch the root locus for your inner loop. Okay. So here input is elevated deflection angle. Here it is a theta dot pitch rate. Okay. Then if we cut this one, it will comes to open loop transfer function. Therefore, your open loop transfer function g of s into your h of s minus 10 into minus 1.2, we will get 12 into s plus 0.585, then we will get s square plus 1.5s plus 1.47 into a feedback is to a rate gyrosensity value. Therefore, initially we make it as a rate gyrosensity value. So then we try to sketch the root locus for this following transfer function. Okay. We try to sketch the root locus for this following transfer function. Okay. So how can we sketch that? We please locate your poles and zeros of your given open loop transfer function. I have one poles that is called as a 0.1 zeros, that will s equal to minus 0.585. Then our two poles, one is s, while solving this equation, s square plus 1.5s plus 1.47 equal to 0. From that we will get poles of your given open loop transfer function. Okay. And okay. Then how can you write the code for this one in MATLAB? We simply write because we already solved so many problems of how to sketch a root locus. So we try to sketch this root locus by using MATLAB. So here it is your, we need to define your transfer function. This is your loop transfer functions. Okay, that is called as your numerator. So I'll use this. For your numerator is equal to, what is your numerator transfer function? The coefficient of s is 1, use open bracket 1, then the constant term is 0.585, then your denominator is equal to, this is, and also we will get s plus 10. Yes, this is a multiplication. This two block is a cascade block. Minus 10 into minus 1.2. We will get 12 into s plus 0.585, then s plus 10 into s square plus 1.5s plus 1.47. Therefore, this your denominator is a combination of two functions here, this function as well as this function. Therefore, it is with two functions. Therefore, use the common convolution of two functions, CONV, convolution of this bracket. Then first you define one function, that is called as a s plus 10. The coefficient is 1 comma 10 comma, next the coefficient is s square is 1 space 1.5, then space 1.47, then you close this bracket. Okay, then your transfer for g, if you define g, BC is equal to your transfer function. Here also the multiple of 12. Therefore, use 12 times 12 star transfer function TF of your numerator comma denominator. Therefore, now I will get this entire save function, the transfer function. Then we need to sketch the root locus. So use the command rlocus, rlocus of your G, rlocus of G. Okay, use this command. You try to sketch the root locus by using MATLAB. Or otherwise, if you want to sketch the theoretically, means you please locate your poles and zeros. So one pole is located S equal to 1 zeros, S equal to minus 0.585. The zeros are marked as a cross symbol, sorry, small circle. This called as S equal to minus 0.45. Then while solving this equation, then another one pole is located at S equal to minus 10. Here one pole is located at S equal to minus 10. Then while solving this equation, S square plus 1.5 S plus 1.47, then we will get the poles. If we solve this equation, then we will get some poles. Then we will look at the poles. Maybe it's a complex conjugate poles. Then we try to sketch the root locus. Okay, next step is we have to verify whether the root locus lies in a real axis or not. Then we take some test point. The right hand side, the test point, total number of poles and zeros lies in the test point is a odd number. Then the portion will be part of the root locus. Then we need to check breakaway and we need to calculate the angle of asymptotes. And the angle of asymptotes is plus or minus 180 degree 2q plus 1 divided by n minus m, where n minus m is nothing but n is number of poles, m is number of zeros. In this problem I have 3 poles, 1 zeros, that 3 minus 1, 3 minus 1 2, then plus or minus 180 degree 2q plus 1. If you put, then we will get plus or minus 90 degree. Yes, I have 3 poles, I have 1 zeros. Therefore only one root locus branches start from poles into ended, that is zeros, s equal to minus 0.485. Maybe these root locus branches start from this pole s equal to minus 10, will go and ended at s equal to minus 0.58. These are one root locus branches. And also we get the angle of asymptotes is 180 degree, plus or minus 90 degree. This is angle of asymptotes line. Maybe my root locus branches, if it is these poles, it will start from like this. This will comes to like this. These were root locus branches. It will pull, these root locus branches start from poles. It will follow the path of 90 degree asymptotes. It will meet at zeros at infinity. The same way these root locus branches start from these poles. It will follow this minus 90 degree asymptotes. It will meet at zeros at infinity. We try to sketch these root locus in MATLAB, and we see. So basic autopilot system with the landing configuration for inner loop. So where numerator is here 0.585. My denominator is composed of 2 functions, that is called as one is elevator transfer s plus 10. Then your aircraft dynamics is s square plus 1.5s plus 1.47. Then your g is equal to 12 times of your transfer function into numerator comma denominator. Then we sketch your that we use r locus command. We will see the root locus branches. These were root locus branches. Okay, so one root locus we need to find out breakaway as well as break-in point also. Okay, so here if you see here, this s equal to minus 10 volts, the root locus branches moves along this direction. It will intersect, or it will maybe break away path. It will meet at 0 setting infinity. Okay, so I'll see here. So these root locus branches will be tell us while varying your rate gyro sensitive value. If you see here in your varying this rate gyro sensitivity, how my closed loop poles of the system will be varying. That we will see in this root locus. So here in this location, my gain value is 1.11. I have a damping, my closed loop system having a critical damped system. There is no overshoot. My frequency is 8.919. So now I'll come to here, my gain. So here my gain means it is a rate gyro sensitive value. If the rate gyro sensitive value is 2.07, I have a damping is 0.94. That is where overshoot is to be 0.014 percentage. So we keep on moving along this direction. If see here, my gain values almost 2.5, 4, 2.48. Okay. My gain value is 2.5. What is my damping? My damping is 0.871. So initially I select my rate gyro sensitive for this basic jet transport aircraft. For landing calculation, I select my rate gyro sensitive values is 2.5. At this location, my damping is 0.871. So we choose, why we choose a high damping? Because this system also having outer loop. So if we choose the damping for inner loop is so high, it will be leads to a close, and also it will that outer loop also having some amount of damping. Okay, that's why we select this my rate gyro sensitive values is 2.5. My damping is 0.871. Okay. Now we sketch the root locus for your outer loop. Then we check your amplifier gain. Okay. So when this rate gyro sensitive value is 2.5, my damping is 0.871. Okay. So in this case, we select your rate gyro sensitive for your complex poles, because this location is to your complex pole. The pole is 5.32 plus 2.99i. My damping is 0.871. Okay. So why we choose your high damping for your inner loop means, suppose that if you consider your outer loop, that outer loop closed loop is tendency to reduce your damping. That's why we select the gain value for inner loop gain is higher value for a higher damping. Because if you incorporate your outer loop system, see here, this is your outer loop system. So if you incorporate your outer loop system, that will pull this where aircraft is to be a lesser damping. So So that's why we select for your rate gyro sensitive value as soon as high value for your slightly higher damping of your as compared to your inner as compared to your outer loop. Okay. So now I will sketch the root locus for their inner loop. Then I select my rate gyro sensitive values. The gain value say 2.5. At the time my damping is 0.871. Okay, so the inner loop having higher damping. Why we need inner loop having higher damping means if you couple with your outer loop, the outer loop closed loop holds tendency to reduce the dampings. So if you initially select the inner loop having lower damping, if you incorporate with your outer loop, it is also reduced to a lower damping value. So if you, the damping is very less, then I have a peak overshoot. That's why we select the gain damping is a higher damping. The respective gain is 2.5. Here damping is almost 0.871. So the outer loop is, if the damping is slightly 0.5 or 0.6, then it is to be a designed for good control system. That's why initially we make it, the inner loop damping is 0.871. That my rate gyro sensitive value selected as a 2.5. So now I go to, while sketching the inner root locus, then we select your rate gyro sensitive value. That means here this SRG, then we can as consider as a KRG, rate gyro sensitive values is 2.5. Okay, my damping ratio for inner loop is 0.871. Now we investigate the root locus for your outer loop system. Okay, and what is your outer loop system? Now we close this first. We close this inner loop. So now the